Welcome back. In this episode, we're diving into remote sensing, a crucial tool for pilots, meteorologists, and flight planners. We'll explore how we gather weather data from satellites, radar, and other remote systems. This helps us see weather patterns and predict conditions that are critical for flight safety. Let's start with satellite imagery. Satellites are crucial for observing large-scale weather systems, including cloud cover, temperature variations, and storm development. They give us real-time data that we can't always get from ground-based instruments. For example, when flying over the Atlantic Ocean, satellite imagery can show where thunderstorms are developing, especially useful when flying at night or in areas with no ground stations. This data lets us plan routes that avoid bad weather. Let's talk about the different types of weather satellites. The Geostationary Operational Environmental Satellite, GOES, is one of the most commonly used. GOES satellites orbit the Earth at a fixed point above the equator, providing continuous real-time weather data over the same area. These satellites monitor things like cloud cover, surface temperatures, and sea surface temperatures. This data helps us track tropical storms, hurricanes, and fronts. In fact, the National Hurricane Center uses GOES satellite images to track storm formation in real time. Next, we have polar orbiting satellites. These travel from pole to pole, covering the entire Earth's surface over time. Polar satellites are ideal for monitoring temperature trends, ice cap data, and precipitation. They provide global data that helps forecasters predict long-term weather patterns. For instance, a polar satellite can show how sea ice in the Arctic is changing, which could affect weather patterns across the Northern Hemisphere. Pilots can use this data to anticipate weather system shifts that could impact their flight routes. One important feature of satellite data is infrared imagery. This shows cloud temperature, which helps meteorologists determine cloud height and density. Warmer cloud tops indicate higher clouds, like those associated with thunderstorms. These are important to watch when planning flights to avoid turbulence or lightning strikes. In addition to infrared, we have visible satellite images. These provide a picture of cloud cover during daylight hours. Visible images help pilots see cloud formation and identify storm systems. They also allow meteorologists to track system movement and development throughout the day. Another key tool is radar. Radar systems send out pulses of radio waves that bounce off objects like rain or snow. This helps us detect precipitation and turbulence areas. Radar data is especially useful for short-term weather prediction and helps us track storms and wind shear in real time. The most commonly used radar system is Doppler radar. This system not only detects precipitation but also measures the speed and direction of rain and wind. Doppler radar helps meteorologists track storm rotation and wind shear, making it an essential tool for tornado and severe storm tracking. Let's consider an example. If you're flying through an area where radar shows heavy rain or turbulent wind patterns, you'll have a better understanding of what's ahead. You can plan for altitude changes or make course adjustments to avoid areas of severe turbulence. There's also weather radar on aircraft. Most commercial aircraft today are equipped with radar systems that allow pilots to see storms and turbulence ahead. This data lets pilots make immediate decisions during flight, such as diverting around storms or adjusting altitude. In addition to weather radar, aircraft are also equipped with pitot-static systems. These systems measure air pressure and speed to give pilots data about altitude and airspeed. While this is not strictly remote sensing, the data collected feeds into onboard systems to enhance situational awareness. Now let's talk about ground-based weather stations. These are often located at airports, providing real-time data about conditions like wind speed, temperature, and humidity. The data is collected and sent to air traffic control and meteorological agencies. In some regions, like the Middle East or Africa, ground-based stations are limited, making remote sensing data even more crucial. Satellites and radar can provide coverage for areas where ground stations are sparse. One of the key challenges with remote sensing is data interpretation. Satellites and radar give us a lot of information, but it's up to meteorologists to analyze it and make predictions. Remote sensing doesn't replace human judgment, it supplements it. Pilots use satellite and radar data in combination with META and TAF reports to get a complete picture of what's happening in real time. By using remote sensing alongside other data sources, pilots can anticipate changing conditions and make safer decisions. Let's talk about how remote sensing helps flight planning. Before departure, pilots use satellite imagery to check for storm systems, cloud cover, and wind patterns. This helps determine the best route, avoid turbulence, and identify potential alternate airports. During the flight, pilots rely on real-time radar data to detect precipitation or severe turbulence in their path. If storms develop while en route, radar can help pilots adjust altitude or course to minimize the impact. And finally, after the flight, meteorologists use remote sensing to analyze weather patterns and storm movements. This data is critical for future flight planning, as it helps forecasters predict weather for the next few hours, days, or even weeks. Let's wrap up today's episode. Remote sensing, through satellites, radar, and other technologies, gives us the tools to see and predict weather patterns, even in areas where traditional weather stations are unavailable. For pilots, it's a vital tool for making informed decisions during flight and ensuring safety. In the next episode, we'll continue with remote sensing, Part 2, focusing on data analysis, integration into flight systems, and new technologies that are revolutionizing weather forecasting and flight planning. See you in Meteorology number 49, Remote Sensing, Part 2.